Here's a question for you. What's one thing you can do that a multi-million-dollar robot can't? Fold your laundry. Yeah, it sounds almost like a joke, but for a machine, handling soft, floppy, unpredictable things, clothes, cables, even food, is a massive, massive challenge. Today, we're going to break down a new AI system that's finally starting to teach robots how to solve this squishy problem.
Just take a look at this. It's a robot folding a towel. It's a chore most of us do on autopilot, without a second thought. But for this machine, what you're seeing is a monumental leap forward. You see, unlike a solid block or a metal gear, a towel doesn't have a fixed shape. And that very unpredictability makes it incredibly difficult for a robot to figure out how to grab it, manipulate it, and just understand it.
And this really gets us to the heart of the matter. Why is something so mundane, like folding laundry, considered a grand challenge for the entire field of robotics? The answer, it turns out, isn't really about chores. It gets to the very core of how robots see, understand, and interact with our physical world. Okay, so to understand the solution these researchers came up with, we first have to really appreciate the problem. And the problem, to put it simply, is floppy things. They just don't play by the same rules that robots are used to. Robots are absolute masters of the rigid world. A box, like you see on the left, has a clear shape, its physics are predictable, you can describe it with just a few numbers. But a deformable object, like that piece of cloth on the right, it has a practically infinite number of possible shapes. Every tiny fold, every little wrinkle completely changes its state. And there's no single fixed point for the robot to anchor its understanding. It's a total mess. So how on earth do you teach a robot to handle infinite possibilities? Well, the traditional way is something called imitation learning. A person literally grabs the robot arm and shows it the task over and over again. But just imagine trying to demonstrate every possible way a towel could be crumpled up. You'd need thousands, maybe even millions of examples. It's incredibly slow, it's super expensive, and it's just not practical. This right here is the learning bottleneck. So to break through this bottleneck, researchers developed a new system, a new pipeline called soft MimicGen. And the core idea is brilliant. Take a tiny number of human demonstrations and intelligently multiply them into a massive, diverse data set that the robot can actually learn from. Okay, so here's the high-level view of how it works. It all starts with a human providing just a handful of demonstrations inside a simulation. Then soft MimicGen takes over and gets to work, automatically creating thousands of new examples, where the object is in a slightly different starting position every single time. And finally, the robot trains on this huge synthetic data set, learning a skill that it can then transfer out into the real world.
So how does all that actually work? Well, the first key insight is to fundamentally change how the robot sees the object. It doesn't perceive a towel or a rope. It sees something way more abstract, more mathematical. And this is what's called a node-based representation. Essentially, the system doesn't see one single thing. It sees the towel as a big collection of hundreds of individual 3D points or nodes. And this collection of points is what we call a point cloud. So the state of the towel at any given moment isn't its overall shape, but simply the current 3D position of all of these nodes. This is the key that lets the system track the object's configuration no matter how crumpled or stretched out it gets. Okay, so the robot sees the towel as a cloud of points. Great. But how does it know what to do when that cloud of points is in a completely new arrangement it's never seen before? This brings us to the second, and honestly, the most critical insight, a concept we can think of as a shape-shifting warp. Now, the technical term for this process is non-rigid registration. Let's walk through this diagram together. The system analyzes the point cloud from the original human demonstration. That's the blue towel on the left. Then it compares it to the point cloud of the new towel the robot is actually facing, the red one. And what it does is mathematically find the correspondence between them. It figures out that, for example, this point on the blue towel's corner matches this point on the red towel's corner, even though they're in completely different configurations. The best way to picture this is to think of a smart stretch and squish tool in a photo editor, like the warp tool. But instead of just manipulating pixels on a 2D image, the system is calculating a transformation for real 3D physical space. This mathematical transformation is what researchers call a warp field. So here's the full process, step by step. 1. The system observes the new object's shape as a point cloud. 2. It registers that new shape with the original demo shape, finding all those point-to-point correspondences.
3. It generates that warp field, basically a set of instructions on how to stretch and squish space to get from the original shape to the new one. And 4, this is the real magic, it applies that exact same warp to the robot arm's original movement path.
And this right here is the result of that warp. The light-colored path is the original movement from the human demo. The warp field takes that entire path and transforms it, creating the new, dark-colored path that you see here. This new trajectory is perfectly adapted to the new position of the towel. And just like that, the robot has a brand new, successful example that it can learn from, generated completely automatically. This all sounds incredibly clever in theory, right? But the real question is, does it actually work? Let's take a look at the results.
The results are, to put it mildly, dramatic. On a task of shaping a rope, the previous state-of-the-art system, which was really designed for rigid objects, only succeeded 8% of the time. It just couldn't handle the rope's flexibility. But soft MimicGen, using that non-rigid warp we just talked about, achieved a 98% success rate. I mean, that is an absolutely astounding leap in capability.
And this table tells the exact same story across several different tasks. If you train a robot using only those few initial human demos, the success rate is just abysmal. We're talking single digits. But when you train it on that huge data set generated by soft MimicGen, the performance just skyrockets. For rope shaping, it goes from a paltry 2% to a perfect 100%. For a super delicate surgical threading task, it jumps from 5% to nearly 99%.
And what's really cool is that this isn't limited to just one type of robot or one specific task. The system is incredibly versatile. It's been shown to work on humanoid robots unfolding towels, industrial arms manipulating ropes, bimanual arms packing bags, and even these high-precision surgical robots that have to handle soft tissue. And just to be super clear, this isn't just a video game. The skills that are learned in that clean, controlled simulation are successfully transferred to a physical robot that's dealing with all the messiness of the real world. This sim-to-real transfer is a huge, huge milestone in robotics.
So, the technology is obviously really impressive. But what does it all mean? Why should we care that a robot can finally fold a towel?
Well, it matters for a few huge reasons. First, it absolutely smashes that learning bottleneck, which drastically reduces the human effort needed to train robots. Second, it unlocks the ability for robots to learn all sorts of messy, real-world tasks that were just out of reach before. This is a massive step toward building general-purpose robots, not just machines that do one thing. And what's really interesting is that this method even works on rigid objects, which means it could be a kind of universal solution for how robots learn. Ultimately, this isn't just about laundry or ropes. This research represents a really foundational step towards creating robots that can finally leave the superstructured environment of the factory floor and actually begin to operate safely and effectively in the messy, unpredictable, and often squishy world that we all live in. And that kind of leaves us with a final thought to chew on. Now that robots are beginning to learn how to handle the unpredictable, everything from folding clothes to maybe one day assisting in surgery, what's the first messy job you'd want to give them?